Hello everyone. My today's topic is open and closed functions in a topological space. I Karan of class 5.6. My roll number is 5323 and I am presenting this topic today. So we come at a definition of open function. Open map is a function between two topological spaces that maps open sets to open sets. For example, there are two functions like x and y. Okay, function domain of a function is x and it goes to y. That is open if for any open set u in x, the image fu is open in y. Here we see that u is a subset of x and u must be open for its image to be open in y. Got it? Okay. Now coming on to closed function. A closed map is a function that maps closed sets to closed sets only. Okay. A map may be closed, open, both, or neither. Both in the case of phi and real numbers, and neither also in that case. An open map need not be closed, and vice versa. Now, an open map is the complement of a closed set, and vice versa. It also means that thing. Open and closed maps are not necessarily continuous. Now coming on to continuity. We know that a function is continuous if the pre-image of every open set of y is open in x. Like pre-image, what is a pre-image? Pre-image is the image of, like, a function is defined from x to y, then fx, that is in y, is the image of x, but pre-image is the image of y in x. Okay, so every open set of y is open in x. The pre-image of every open set of y is open in x, then a function from x to y is continuous. Further, continuity is independent of openness and closeness in the general case, and a continuous function may have one, both, or neither property. Like it may be closed, it may be open, or neither. Also, this is the fact in the case of metric spaces we dealt with our in our previous classes. Although their definition seems more natural, open and closed maps are much less important than continuous maps for obvious reasons. We don't study open and closed maps for like in deep, but we do study the continuity, and continuity is dealing with the surjectiveness, injectiveness, and bijectiveness. Now coming on to the properties of open and closed maps or open and closed functions. And here remains the fact that equivalently, if the pre-image of every closed set of y is closed in x, then also the function is continuous. Like it is not necessarily that always an open set, like pre-image of every open set of y is open in x. It could be if the pre-image of every closed set of y in is closed in x. Okay, a function. So we are dealing with the properties of open and closed functions here. A function from a function f from x to y is open. So here it is an if and only if condition. Like for if this exists, then this must be like this is necessary and sufficient condition. For every x in x, every neighborhood u of x, however small, there exists a neighborhood v of fx such that v is subset of fu. What does it meant to say here? Like we have two domains. One is a domain and another is a codomain. That is y. So x in x there is a neighborhood u. Like consider a point x in x, the open set X, and the neighborhood of that small x is a point, the neighborhood of that point X is U. So there must exist a neighborhood V of Fx, that Fx is the image of X in the Y codomain. So the condition for the function to be open is that V, that is the neighborhood of Fx, that is image of X, must be the subset of Fu, that is function of U. Function of U here is the uh, image of neighborhood U. It suffices to check openness on a basis for X. That is, a function f from X to Y is only if is open, or if and only if it maps basic open sets to open sets. Like here it says that a function is open if and only if it maps from closed open set to open set, and it is closed if it maps from closed set to closed set. Thus the proof. The composition of two open maps is open again, and so is the composition of closed sets. Composition of closed sets is closed. Here the composition means the mixture or the product of two open maps. The categorical sum of two open maps is open, and for two closed maps is closed. The categorical product of two open maps is open. However, the categorical product of two closed maps need not be closed. Okay, these are certain results that we need to remember for the closed or open sets. Uh, you, I hope you all are clear with the facts about your categorical product and categorical sums and compositions. You all must be aware of this all. A bijective map is open if and only if it is closed. A bijective map, that is 1 1 and on 2. So 1 1 and on 2 function is open in and if and only if it is closed. So for the bijective function to be open, it must be the image of it must be closed. The inverse of bijective continuous map is a bijective open or closed. It remains the same. Okay. A surjective open map is not necessarily a closed map. Like a surjective is what is a surjectiveness? If for each y there exists a x in the domain, that is the x need not be unique, but there should exist a x. So likewise, a surjective closed map is not necessarily to be an open map. Like this conditions hold only for the bijectiveness, that if a bijective map is open, then it, if and only if it is closed, and it is closed if and only if it is open. And the inverse, but for the surjectiveness, it doesn't hold that condition. Okay, to so jumping on to the next part, let f be a function from x to y, be a continuous map. These are certain results that are uh, we need to remember this for like uh, not for the proofs, but yeah, they are necessary. If f is a surjection, that is onto, like for every y there exists a x in which need not to be unique, then it is a question map. We are all are aware of the question map. I don't want to explain it, elucidate it further, because it would be a long video then. And if f is an injection, then it is a topological embedding. And if f is a bijection, here injection means one function. Like injection is for every x there exists a y. It need not be, it should be unique. Like the function should be unique. If f is a bijection, then it is a homeomorphism. Homeomorphism, what is an homeomorphism? Homeomorphism is also called continuous isomorphism, that if there exists a continuous function, then inverse of that function is also continuous. In first two cases, being open or closed is merely a sufficient condition, like it is the only sufficient, like if surjection holds, then it is a quotient map. But the converse need not be true, that if there exists a quotient map, then it need not be the surjection. Okay, and so on for the topological embedding, that a topological embedding need not to be injective function. But in the third case, it is necessary and sufficient condition that if and only that if a function is bijective, then it is homeomorphism, and for the homeomorphism condition, it should be bijection too. Now coming on to some examples of the open and closed functions. Every homomorphism is closed, open, and continuous. In fact, a bijective continuous map is a homomorphism. We have already studied this, like for the if and only if condition of a homomorphism, it is the same. And if y has a discrete topology, discrete all the subsets are open and closed, like in a discrete topology, this is the necessary condition. Then every function f from x to y is both open and closed, but not necessarily continuous. For example, the floor function from R to Z is open and closed, but not continuous. This example shows that the image of connected space under, for connectedness, we should see another video for this. Whenever we have a product of topological spaces, that is x is equal to pi. Pi here means the product of xi's, like all the xi's in topological spaces are open as well as continuous. Since the projection of fiber bundles and covering maps are locally natural projections of products, these are also open maps. Projections need not be closed. So projections need not be closed here. On to our last example. To every point on the unit circle, we can associate the angle of the positive axis with a ray connecting to the point with the origin. This function from the unit circle, like in an unit circle, we see that the radius is 1. So we can easily draw or find out the angle it makes with the x-axis or with the help of a ray from origin. So it is defined on the open interval 0 to 2 pi. That it should be bijective, open and closed, but the function, the unit circle need not be continuous. It shows that the image of a compact space under an open or closed need not be compact. We would deal with this theorem later in next chapters. Also note that if we consider this as a function from the unit circle to the real numbers, then it is neither open nor closed. Specifying the codomain, that is y, that is this r here, is essential. But the function f r to r with fx is equal to x square is continuous and closed but not open. So thank you.